Simpsons 1/3 rule. Okay, so to curve fit using quadratic equations, we would need 3 points. I'll just look at just 3 data points first, and then I will extend this to an entire function. So let's consider 3 points. This is f of x, this is x. And let's say that these points are xi minus 1, xi, xi plus 1. And of course, you know the values at these points, you know, fi minus 1, fi, and fi plus 1. Okay, so what we'll do is we will approximate the curve using a quadratic polynomial. So that form, let's say that's p2x, and I could choose ax square plus bx plus c, but just to make my life easy, what I'll do is I'll choose it to be x minus xi square plus b x minus xi plus c. And the benefit of using something which is sort of translated by xi is that when I substitute the value of x equals xi, you'll see that you'll only get c, right? So you'll basically be able to figure out one of the constants. This one should be the value of the function of f of xi or f of I. You could then put xi minus 1 to get xi minus 1 minus xi square plus b xi minus 1 minus xi plus c equals fi minus 1. And then you can also put the value at xi plus 1 minus xi plus b xi plus 1 minus xi plus c equals. So we have 3 unknowns, a, b, and c, and we have 3 equations for the 3 unknowns. So we can effectively compute the value of a, b, and c. So 3 equations, 3 unknowns. So it turns out that the constants a, b, c are given as follows. Solving the system of 3 equations, 3 unknowns. Here we have a equals f of I plus 1 minus 2 of f of I plus f of I minus 1 divided by 2 delta x squared. Looks like the the second derivative, right? And then we have b equals fi plus 1 minus f of I divided by delta x, and then c equals simply f of I. Here delta x is, so we assume that there's uniform grid, which means that xi plus 1 minus xi plus 1 minus xi equals xi minus xi minus 1 is equal to delta x. Okay, so what we have done here is effectively computed a, b, and c. So this polynomial is now completely known. We know what that polynomial looks like because we've used the fact that passes through those 3 points. So once you approximate the curve with a polynomial, what you do is you integrate this, treating it as that approximation. So the next step is just to integrate the equation. So I'll substitute this particular equation, this quadratic approximation, and integrate from limits. In this case, the limits are xi minus 1 to xi plus 1. So I need to find this area. Okay, so this is what I get. So what I'll do is I'll integrate from xi minus 1 to xi plus 1, essentially this expression, right? And a, b, and c are known. So when you integrate this expression, and I will not get into the details of the integration, but this is easy to integrate because it's a quadratic equation. You end up with I, and let me call this I of I, where I denotes that the center point is I. So I is 1/3 f of xi minus 1 plus 4 times f of xi plus f of I xi plus 1 times delta x. Sometimes, and this is probably a better way to write it, it's like a shorthand, we'll write this f of x I minus 1 as f of I minus 1 plus 4 times f of I plus f times I plus 1 delta x. You could write it either way. I just think that the second one is easier way to write it down. It is cumbersome. So this is called the 1/3 rule, which now makes sense because you see that factor 1/3 appearing. It's just a random name. You could also, I would call it 141 because the 141 comes in the numerator, but they call it 1/3 rule. Okay. Okay, so this is what you get only when you look at 3 points, 1, 2, 3. Now we want to, in general, estimate the integral for a bunch of points. So let's take a bunch of points. In fact, I'll take n equals 8, write down the formula, and which will help you to generalize to more number of points. So here is, okay, let's say that we decided on, let me check, 1, 2, 3. Okay, green is better. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's, so this is F0, F1, F2, F3, F4, F5, F6, F7, F8. Okay, okay, so what we are doing here is look at what we have achieved by using just 3 points. We need 3 points to do the integral. So what we need to do here is we need to take this integral in, we need to take 3 adjacent points. So let's take this and this. So this would be the first one, right? Because I'm going to curve fit quadratic on those 3 points. Next, I will take the next 3 points, fit the quadratic. Next, take these 3 points, fit another quadratic. And then finally, take the last 3 points and fit another quadratic. Okay, now that we have these we can write a formula. What we have to do is we take the first 3 points and then write that formula we wrote down earlier. This formula is here, 1/3 fi minus 1 plus 4 times fi plus fi plus 1. So if you write it down, we get 1/3 f0 plus f 4 times f1 plus f2. That's the first region. Then we have plus 1/3 f3 plus 4 times f4 plus f5. 0, 1, 2, 3, 4, 5. No, my bad. Sorry. This should be 2, 3, and 4, because you start at 2, then you go to 3, then 4. Then 1/3, 4, 5, 6, and then 1/3, 6, 7, 8. Okay, just move it to make some space. Okay, so that's that. Now let's just try to sum this up. Okay, so the 1/3 will come out. By the way, I forgot to put a delta x here. There should be a delta x, which is missing. Delta x being this. And the same thing here. Delta x, delta x, delta x. So delta x divided by 3. And here we write down all these terms. f0, 4 times you know what, it's easier if I do it this way. So 0, 1, this will get multiplied, so summed with this 4. So looks like f0 and f8 don't really have anything to add up with. So let's just write those two together. Next, look at all the terms which will have 4. So 4f1, 4f3, 4f5. So 4 times f1 plus f3 plus f5 plus f7. And last, let's look at this f2, which will sum with f2. So twice f2, then we'll have f4 plus f4, f6 plus f6. So we'll have 2 times f2 plus f4 plus f6. Okay, I think I've covered all the terms.
Excuse me, I have a question.
Yeah.
Let me take a look here. Why do you multiply the F2, F4, and F6 by 2 one more time?
So
Because there are 2 of them.
2 of them, yeah, right. That's right.
Right, thank you.
Okay, so we got this expression, okay? And our goal to get this is to generalize this. What if there was n such intervals? So from this pattern, okay, something, by the way, something to note here. If there was a f9, let's say there was an f9, you just cannot do this integration because you need 3 points. You need pairs of 3, right? So you can't do f8, f9, and you need an f10. So this method will not work if you have odd number of grid points. So it only works for even grid points. So here in this particular case, this is kind of very important and really a point of confusion. Here n is 8. It is even. Okay. But if you look, I've started counting from 0 all the way to 8. So really there are 9 points at which I'm doing this. So there are 9 n plus 1 grid points. Okay. So if there are n plus 1 grid points, and grid point is all those crosses are grid points, you need n to be even. Okay. Super confusing for people when they do this. They're confused which one should be even. It should always be n which is even, where n is the last number there. Of course, you start from 0. Okay. Now, if I want to start from 1, then the logic will change. It will be f called f7, which means it will be odd. But let's just stick to this convention where we start counting from 0, go all the way to n equals an even number, and that's where you can apply Simpson's 1/3 rule. You cannot apply if n is odd. So that's like very important. Okay, n has to be even. Now that's in place. Let's write this summation. We have delta x divided by 3. Okay, so if n is even, we've checked that. How do we write the formula? We can actually look at this formula here, which I wrote for just n equals 8, and try to generalize it. Clearly, we'll always have f0 plus 8. 8 is the last number, so it should be fn plus 4 times. You can see what goes in there. That's 1, 3, 5, 7, which means every odd term is appearing there. So instead of writing it that way, which is summation, I just use a summation sign, and I put 1, 3, 5, all the way to n minus 1, right? Last one is 7, which is 8 minus 1 or n minus 1. Fi plus twice summation. Now you can see what you see there is 2, 4, 6, right? 2, 4, 6. You don't get the last one. The last number doesn't show up. So we'll write this as 2, 4, 6 goes all the way to n minus 2 Fi. Okay, so that is the formula to use. Okay, so this is the formula you have to use. And just remember that n has to be even. Okay, now that we have got a formula for the Simpsons 1/3 rule, let's look at a still better approximation. It's called the 3/8 rule. That will be the last one. So the fourth one, Simpsons 3/8 rule. Okay, so like before, uh, just to give you an idea of how this derivation proceeds, we're trying to fit a cubic equation through the points. So if there's a curve like this, we'll randomly assume that the second point is Fi, or rather, let's just put it as xi. This is xi plus 1, xi plus 2, and xi minus 1. Okay, so we'll assume P3 of x as ax minus xi cube plus bx minus xi square plus cx minus xi plus d. So we see that we have 1, 2, 3, 4. So we have 4 unknowns, and we can generate 4 equations. How we generate them? Well, we know that it passes through xi, xi minus 1, f of I minus 1, xi, fi, xi plus 1, fi plus 1, xi plus 2. Okay, so the same trick, you have to make it pass through these 4 points, compute a, b, c, and d, then take the integral. So solve for a, b, c, and d. It's just the same thing. I'm just going to not write down. Then take the integral from xi minus 1 all the way to xi plus 2 of ax minus xi cube plus bx minus xi square plus c x minus xi plus d dx. And then what you get here is going to be the formula for Simpson's 3/8 rule. It comes out to be something like this. 3/8 fi minus 1 plus 3 times fi plus 3 times fi plus 1 plus fi plus 2 times delta x. So let's just put the delta x here. So this is the Simpson's 3/8 rule. The derivation is similar to the other one. We're not really interested in that, but that is the formula. The 3/8 rule comes because of the factor 3/8 on the extreme left. Okay, so now that we have this formula for for 4 points, let's try to generalize this. We in general have to do this for a curve which may not have just 4 points. Okay. So the same trick applies. We will do this for a few set of points, write down a formula, and then see how we can take that formula and generalize it to more segments. In this case, there's a special, just like the other one, we have to actually use an odd number of points. So let's see how that goes. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. F0, F1, F2, F3, 4, 6, F9. So remember, if you take 4 points at a time, 1, 2, 3, 4, this will be our first region. Our second region. Third region. Okay, and then the formula will look like this: delta x, 3/8 delta x. Okay, so I'll do the 3/8 rule now. So remember how the points look. It's f0, so fi minus 1 plus 3 times the next term, 3 times the second term, plus 1 times the fourth term. So f0 plus 3 times f1 plus 3 times f2 plus f3. Then we have f3. I start from f3 plus 3 times f4 plus 3 times f5 plus f6. And finally, f6. You can look here. f6 is right here. And f3 was here. So you start with f3 and then f6. 3 times f7 plus 3 times f8 plus f9. Okay, before we move on and try to sum that up, remember one thing. If I put a 10th point, f10, I'll be stuck. I can't really use 2 points to integrate because that point is going to be, is not, I can't fit a cubic now, right? If I put another point here, f10, f11, that will not work too, because now I have just 3 points. Okay, I need to put a fourth one, F12, and now I can connect it, right? So this method actually only works when n, where n is this number, is uh, odd. So actually, multiple of 3, my bad. Should be a multiple of 3. So n equals 3, it should always be a multiple of 3. Okay, so the formula will look like this: 3/8 delta x. Let's sum this up. So again, I'll do the same trick, which is first term and the last term are standalone. So I'll just put them like this. Then there is 3f1, which is by itself. There's f2, which is by itself. F3, F3. So there'll be twice F3. And F4, F7 are by themselves. So it looks like the pattern which emerges, there are terms which have 3 in it and then terms which have 2 in it. So the terms with 3 are 3f1, 3f2. So I remove the 3 up. 3f4 plus f5 plus f7 plus f8. And then there are terms with 2. So the terms with 2 would be f3 and f3 comes out, f6 and f6 comes up. So we have twice f6 plus, sorry, f3 plus f6. And I think that's about it. Okay, so with that, we can try to come up with a very general formula for n. Okay, the first term and the last term is the first one, which I've multiplied by 1. 3 times. Now what we see here is this pattern. We have f1, f2, f4, f5, f7, f8. So instead of writing it as a single number, I'll write it as fi plus 1, where I only have to be bothered about putting the index for the first one. So here I would be what? 1. So when I put I equals 1, it actually captures the first and second term, because it'll be 1 plus f2. Then I need to put 4, right? 4 and 5, then 7 and 8. So here what happens is, here I will be 1, 4, 7, all the way to 8. 8 is actually, we had 9 terms. 8 is 1 less than 9, so n minus 1 plus 2 times summation fi. Here we see it's 3, 6. So it looks like it's a multiple of 3. So 3, 6, all the way to n minus 3. So this is our general formula. N is multiple of 3. Okay. Okay, now with that, we can apply this on the, we'll use the same problem which we did last time and see if we can get a better answer. So the problem we did last time was this one. And it's 1/3 rule. And the analytical calculation, we had done it last time. It was 0.3333. So we know the answer is 3333. And remember when we did this with both methods, rectangular trapezoid, we had some error. It was not accurate.
Hey,
Yeah.
one more thing.
Yeah.
Can you just go back to the 3 example one more time? I want to see it.
3 example.
The 3 example.
3/8. This one you mean?
Yeah, I just wanna write it.
Oh, sure. Okay. We did a lot of work for this, the previous problem. So we'll just reuse that. It had the same n equals 6. So why not use it? So just to save some time, I'll just copy this table, which we came up last time for n equals 6, because that won't change. So if you know, it might be easier to just reference it instead of trying to recopy it all over again. Okay, and then to start, Simpson's 1/3 rule. We just take the formula which we wrote down. So this is the formula. Is it here? Right? So 1/3, well, not this one, here. F0 plus Fn 4 times 1357 plus 2 times 246. And n equals 6 here, 6 being an even number, so it works out. Let's go and then write down the formula based on that. So it comes out 1/3 delta x f0 plus f6 plus 4 times, you can see here, sorry. So 4 times f1, f3, f5. And then if you go back here and see, it's 246, twice 246. So twice 2, 4, and 6 won't come because 6 is already accounted for here. Okay, now what you do is essentially just sub in the values. I've already give you f1, f2, f3. So you know the values, you can just sub that in, and you get for 1/3 rule, the answer comes out to be 0.3333. So for the 3/8 rule, it's 3/8 delta x. And then we go to this formula, and we see it's f0 plus fn, so the first and the last term. So the first term is f0, last term is f6. And then we have 3 times 147. So 7 doesn't exist, so it's just 1 and 4. So we do f1 plus f2, and then f4 plus f5. f1 plus f2 plus f4 plus f5. And then finally, we have twice I goes from 3 to 6, so there's no 6, just 3. So 2 times f3. Okay, so now it's just an exercise of subbing in the values. All the f's are here. So if you do this, you get 0.3333.